Well, hi, and thanks for joining me here in my shop this morning. So I'm planning on running 20 of these 6SN7 tubes that I've been testing in various testers through this one and measure the mutual conductance, or the GM, for both halves of each of these tubes. So to facilitate that, I've got the numbers written here for one half of the tube or the other half of the tube, so I don't have to send my eyes to the computer screen and all the attendant risks of making errors by looking back and forth. So I could just look here, because I'm going to have to flip these numbers each time I test a tube. So that's what I'm going to be doing. Why don't we just go through the first one here? This is tube number 1. So let's get things going. I finished testing all 20 of these tubes, 20 or 21 of them, through the ICO EM tester. Ready? So that's trying its best to get right up to a top number 2. That's 90. That would go as 92. And I wanted to do the same on this, but so far the EM test I tried on here makes the needle pin up against a problem spot in the meter movement, and I'm just anxious about sticking the meter permanently in a position there and basically ruining the whole tester. So I stopped doing the EM test. I think we're ready again. Here we go. Oh my God. Whack. Oh, you know, where's it gonna go? Okay, you're plugged in, power on. You may have seen the fuse light come on briefly. It's just like the dim light bulbs I regularly use. It's doing exactly the same thing. Check the filament voltage, 6.3, and we are set CGGG, which I'm quite sure is the right thing, CGGG. Okay, so we'll pop in the tube here. There we go. And we'll double check these numbers. 02016, 02014, rather. 4, yeah, why am I saying 6? 14202. What? Oh, down here. 25600, 25600. Everything's set correctly. Okay, we'll check the line. It's high this morning. Bring it down. No, I don't see that this tube is heating. Oh yeah, it's heating up. Okay, line adjust is good. We'll set the bias now. The bias should be 3.6. 3.6. Right there. And we'll check the current on the tube. Current through the filament. And well, that's kind of interesting. This is reading a little high. You know, when I think I put all these tubes, when I put them through my own test jig later, I'm going to measure this filament current issue, voltage issue very carefully, I think, because it seems like there's some variations here. Okay, but there's definitely roughly the right amount of current flowing in there. Bias is set, line is set, test time. There we are, and so we'd be reading on the 8 scale. So this is reading 1.6, about 1700. So GM is 1700. Just going to mark that down there. 1700. Okay, now we change the settings to this set here, 14202, 14202. 2, 0, 2. And the lower one, all we do is change this one to a 0. 1, 4, 2, 0, 2, 0, 5, 6, 0, 0. Okay, so we're ready to test the other half of the tube. Yikes. Quite a different reading here. So on here, I would make this out to be 600. 600, whoops. 600. Let's check the bias voltage here. 3.6. It's pretty much where it was. Test. Let me just take a peek on our spreadsheet here and see how that adds up. So this was previously tested and the GM was found to be high on both sides. 3,000, 2,500, 2,600, 2,300. Previously, this tube in this tester was 22 and 2,100. Oh my god, what's going on here? So I've tested this. This is tube number 1, and I've tested it in here once already. I think it's such different readings. Okay, this is, again, I'm just trying to kill myself with getting this correct. CGGG. This control means nothing. And it's 02014. Sorry, I'm on the second set. 14202. I got a 0 here. There's a mistake. That's a mistake. 14202. 14202. I can check this thing over and over and still have an error in it. Because I'm shooting a video, I'm not thinking very hard. So this should be 0. So this is correct now. Well, that's a little more like it. Getting the kind of reading I would expect. You know, if you're doing a test and you get a reading that's close to what you expect, then you think the test is good and you're done. Boy, that's a big mistake. That's why I'm doing multiple tubes on multiple testers, to try to eliminate the possibility that things look like they're working when they're really not. Okay, so reading this carefully now. This 2000 almost exactly. Just a hair under 2000 there. That's a little more like it. 2000. But let's go back to the other reading now. See how many mistakes I can make. 02014. 02014. And then this becomes a 2. 256. Okay, I think I can set 5 switches. Here we go. So, and here we're reading. That would be 1700. 2000 and 1700. 2000 and 1700. Previous readings were 2200 and 2100. Well, another whole thing about all this tube testing is the repeatability of it. And I haven't really, poked into that until really just now. So here I am unable to repeat the test. Well, let's see, for sure we got full voltage on here. It wouldn't matter anyway because I have a line check. The line is low. How did that get so low? Let's bring it back up. Okay, that's a little better. Bias voltage, now the bias has gone high. Bring it back down to 3.6. Let's check the line again. Maybe I got to do this line thing a little more carefully. Don't know how it got quite so far out of whack. 3.6. Okay, we're ready now to test. Test. Wow, we got quite a different reading. Boy, oh boy, oh boy, oh boy. Again, this just shows you how tricky it is to get really accurate readings. If you want an accurate reading, most of the time we're using tube testers to find out if the tube works at all. I mean, you're just trying to get a go, no-go sort of thing out of it. But if you're trying to do the precise thing, like watch, I'll just wiggle the bias a little bit. No, that's not too sensitive. Now I have to check it back. Bias 3.6. Right there. Test. So now we are reading 2100. I would say almost 22. So 2150 if I go really accurate on there. 2150. And then we'll do the other side again. Just be a little more careful here. So it's 14202. 14202, and then we change this 1 control to 0. Now we're set, but what we're going to do is we're going to check and see if something funny has happened here with the line voltage. Not really. Bias voltage 3.6 right on, ready for the test. And this time the test comes up to, again, on the right scale. This is like 20, almost 2600, so it's 2550. 2550. Yikes. So I could be looking for some kind of precision out of these machines that really cannot be achieved, not one like this. 2550. So now that compares to 2200 and 2100 done previously. 2150. This 2550 seems impossible. We're on the 823. It's really 2500. It's right there. We'll just go back and check the line again. I'm going to do a line sensitivity check there. That's okay. Bias is still 3.6. I'll vary the line voltage a little bit. Not too much change for quite a range on the motion here. Set the line properly again. I don't have 3.6. 3.4. 3.6. Now I'm getting 6,000. A GM of just 5,900. I can't even repeat the test exactly right in front of me, right now. I cannot make it that repeatable. So not to get too many stars in my eyes here on this. Okay, so we beat this one all to heck. 2150 and 2500. So I'm gonna write that in here alongside the earlier readings. Probably the earlier readings I was not being as careful as I am now. To explain why they're out a bit. 2550, and but you know, those readings I took just now compare favorably to the to the others in the ratio between the two readings. Okay, I think we're ready to get going, so I'm gonna carry on here. I'm not gonna video anything, I don't think, unless something really weird starts happening. And away we go. I've made it all the way to tube number 17 without anything kind of weird happening, but something started now. So just a quick check here of the numbers. Again, 0, 2014 25600. The numbers are set correctly. I watch my test. When I hit the test, watch the fuse light. I'm going to put the last tube back in without changing anything. Is there something funny going on? I stopped for a while, had a cup of coffee, or drank some more coffee. Did something happen? What were those cats up to? Are they doing something funny in here? Or has that tube gone defective, which is kind of weird because it stood up to quite a few tests up until this point. Here we go. So look at that. So we're getting a regular response, no fuse indication, nothing. So here's what I'm going to do next. Put this guy back in. Okay, I'm going to put this onto the short test. Run through the short test now. According to the guide, 7 and 8 should light the short light. So here we go, just 7 and 8. 7, 8. You know, I did this a moment ago and I got shorts up here. Test. This isn't in all the way. Yes, it is. Test. Okay, so while I'm doing the short test, the heaters are turned off, so the tube's just warming up again. Wait a minute, it's behaving normally. Well, that's why I started the camera, because weird stuff was happening here. I don't know. What was that? Oh! There's some kind of intermittent problem with this tube. We go back to this 5. There, the short has come back. Okay, so we can fiddle with it like this. The short is not going away. So this tube out, put the other one right in. No short appears. Okay, so this guy, I got to declare him to be shorted. Funny, it should happen partway through the testing process. Number 17, short. Okay, that's interesting, I guess. Okay, here's another one worth videoing. This is in fact tube number 23. This is the last tube I'm testing. And this one I have tested for GM in this tester already once. So I'm going to do it again. We'll be able to compare. Repeatability is still an issue with these things. I haven't done anything to prove repeatability. So let's give it a go here. It's all set. Okay, so wow, it's barely coming up. Let's just double check a few things here. Align. Okay, bias still on the money. So this is the test result right there. Barely comes up on the meter. So I would say that's 350. 350. So previously this tested at 400 in this tester. So let me just write this in correctly. Now we'll do the other half of the tube. In this case we're getting about 1150 on there. 1150. 1150. Last time was 1200. So we're getting slightly lower both times. Slightly lower this time around than last time around. 1150. Great. So a little more to do here. We have another whole tube tester to bring up, do the GM test through these 23 tubes, and then I've got to do them all in my own jig, which is going to take a long time. So, but it's coming along, and I think we're going to have some really interesting statistics to study up on when I get this done. Okay, I think we're ready to start with another tester. So let me get out tube number 1. Here it is, tube number 1. This is all set. I've written the numbers here. I don't have to look down here and get confused. I can just look up here and get confused. It's in. There we go. So I only have just one row of switches here. That's a little simpler than the precise tester. I have to change all of them but one. The 0 can stay 0. Screen can stay 0. There's no screen in this tube. That would be why. You can see up here where it says filament, grid, plate, screen, cathode, suppressor. It's kind of neat. Okay, I think we're probably ready to start. Let's see if I can remember how to work this. So we're going to skip the short test until I get to the one or two tubes that have had problems with that before. Why does this look so not hot? It's heated up. P4 is the guy. So P4 reading on the top scale here, the 3000 scale. So that's 2050, I would say. 2050. Okay, 2050. I'm just going to write it in over here. Tube number 1, GM. This has been done before. This again goes to repeatability. The last time I did this, I got 2300. I get 2300 before and 2050 this time. Let's see, I did not check the line voltage. Well, there's really not much there. Bias is right on 23. And the English, which we're not using, the English controls the good-bad scale. And we're on the 3000 scale here. Oh, let's try it again. Well, 21 now. 21. 21 as opposed to previous test of 23. Okay. 2103. With a 5. That's the change. 2500. Put that in here. And so before we had tested it at 2600. That's interesting. So but the variation between the two sets of tests is bigger than you'd expect when you do a test again. If it varies, the A and the B are going to vary the same percentage from the original A and B, but that's not what's happening over there. So again, can you tell if a tube is good? Well, sure. I haven't done a single test here which has told me a good tube is bad or a bad tube is good. I don't think a single test has happened like that. Okay, so I'm going to carry on here. I've got 22 more tubes to work my way through here. Okay, I've got tube number 17 here in the Stark tester, and this tube in the precise tester showed up a short. It seemed inconsistently during the short test. It seemed to be there, then it wasn't there. So a little bit of a mystery. I put it in here, and I'm going to set the switches for this setting here, 2103. Because I'm going to show you, first of all, are there any shorts? So you watch the short bulb. It's behaving as if the tube is normal with no shorts. I'm going to take the test. 1500, it's not particularly good. 1500. We'll now switch to the other setting. 4506, the 1 there. We'll now repeat the short test. Aha! Okay, so you know what I did? Here's a lesson. So I put the tube in, set for 1/2 the tube, short test, no shorts. Set the switches for the other half of the tube, push the button, and obviously there's a short. So clearly, you got to, if you really want to do this properly, you got to do a short test on each tube section if it's a 2-part tube or 3-part tube, which makes perfect sense. So this tube is out. because it's reporting shorts. Shorts, you do not want to push the test button on a tube with a short in it. No, 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 no. So number 17 is at the end of its road here. So I've completed all the GM tests through the commercial tube testers, and I have all that charted out. And I can see there's 3 or 4 tubes that are cockeyed. Either one half tests really poor, the other half tests really good. So I'm going to take those interesting tubes and I'm going to run them through my own test jig here. I'm not going to do all 23 tubes through this. It would take me probably the rest of my life. So, but I can afford to do 2 or 3 in here and have that information for comparison too. So that's what I'm up to. I've got tube number 13, I think it is, in there. Well, what I'll do is I'll record this particular tube. So it's heated up. Current's slightly high here. It's time to get the negative bias onto the grid before we go too far. There we are, -8. -8. There we go, -8. Just drop this a touch. Goodness knows, in the commercial tube testers, the current flow through the heater is not well controlled at all. I'm sure it's different in every time you pop a tube in. So we're reading B+ here. We would be. If I do that, and then we turn it up a little bit. Let's try this. Got about 100 volts out here. Mine is not showing up. Oh, could be partially because this is unclipped here. Oh, this is. Oh. A couple of clips have fallen off. Okay, now we're in business here. So we want 150 volts. I can get exactly 150 by using this meter. Here we are, 78. $150 volts is what we're looking for. How about I get out of the shadow? How did I get in the shadow? Okay, 250 on the plate. I'm keeping my eye on this current meter down here too. As everything is working right, we should see about 8 or 9 milliamps at 200. When we get to 250 volts. So this is a test in itself. If I take every tube and we're to put them in exactly the same state here, 250 volts on the plate, -8 on the grid, and 600 milliamps through the filament, I'm bound to get different readings of current flow here for different tubes. So this one is 9.4 milliamps. Now, I'm just going to mark that down. 250, 9.4. Is that right? 9.5 milliamps. DC. Might be able to calculate the plate resistance from that. Okay, now what we really want to do though is put a dynamic signal through the tube. So we want to put a signal on the plate. So what I'm going to do, because we need to know the signal level, I'm going to move this meter onto the grid. I'm going to change it to reading AC also. So I'll take it off the plate and set it to 2 volts AC, and we'll stick it on the grid. Okay. Also change this from reading DC current to reading AC current, just like that. I know from all my experimenting in that this is accurate, even though there's still a DC voltage flowing through it. It's basically, and as I've mentioned numerous times, it's 0.00, so that's 0.02 milliamps showing up there right now. And this, of course, is 0.009 volts. So we'll raise the AC signal. You should be able to see it on this upper display too. We'll raise it up to some set amount here, like 1 volt to start with. Okay. 1 volt AC signal applied to the grid. So keep an eye on the current down there too. Okay, coming up on 1 volt. You can see it on the scope there. Okay, that's 1 volt. So we'll record the current, and we're starting now to do the GM measurement. At 1 volt gives you 2.64 milliamps. 2.64 milliamps. Now we're going to change this to 1.1 volts. Doesn't sound like much of a change, and I suppose it really isn't. It's well, it's at 10%. I guess it is a bit significant. Right up there. There we go. So I've now increased this 0.1 volts, and we read the current down here again. 286. So the GM is the change in the output current divided by the change in the input volts, and then I think multiplied by 1,000. You got to have a factor in there to get the final number. So in this case, I dare show you my powerful calculating sheet here. So we have a 0.1 volt change in the grid, and here we've got a 0.22 milliamp change. It's 0.22 milliamps in the plate. So we divide this out, we go 0.22 milliamps over 0.1, and that's going to come out to 22 moles. What's the symbol for a mole? Moles. Yeah, once again, just because I just skipped from here to here, I didn't actually calculate it. That's usually the spot where it turns out I'm totally wrong. 0.22. I think I'm going to be wrong. 0.22 divided by 0.1. Yeah, times 1,000. 2,200. That's right. 2,200. We won't compare it yet to the other tube testers. We got the other half of the tube to do. So we can leave the setup just as it is. Okay. In other words, we've still got 1.1 volts and 2.87. Okay, that's good. We'll change plates. We're going to lose, I don't know what we're going to, won't lose anything, I don't think. Yeah, we'll lose that meter, but that's okay. We know we got the voltage set properly. So on the other plate now, we'll take, at 1.1 volts, we get, look at that, it's really 1 milliamp. Why don't we go with that? Nice round numbers. So 1 milliamp. Now, what I want to do is I want to reduce this voltage down to 1 to get the 0.1 change. So we'll do that. Down you go. You kind of jumped up there, eh? What's going on? Something funny going on here. I turned it right down to nothing. There's still something there. What's up? Something funny going on here. I can't afford to have funny things going on while I'm doing this. Oh, yeah, that's right. I'm on AC. That's right. Yeah, I was turning the wrong control. I was turning the wrong control. You see, they put more than one knob on these, you know, machines, and more than one knob. I'm bound to grab the wrong one at some point. Okay, back to where we want to go. We want to go, we've got the 1.1, so we want to go to 1 volt. That'll give us the 0.1 change. Back up to 1 volt here. There's 1 volt, and we got 2.33 milliamps. So that would be a change of from 1 milliamp to 2.33. That's a 1.33 milliamp change. That's a lot. This is going to give me something crazy. I'm getting a crazy reading out of this. So, hey, what happened here? What happened there? Oh, talking about turning the wrong knobs. What the heck? Okay, hold on. This is totally bogus. Hopefully I didn't fry the tube there with no grid bias on it for a while. Okay, we're back to doing it again. Proper grid bias. 1 volt AC on the grid. 2 milliamps. Nice round number again. That's nice. So now we'll increase this to 1.1. I'll try and grab the right control this time. This one. I'm overwhelmed with knobs. 1.1. Okay, there's 1.1. And now the current is 213. So that's an increase of 13. That's 1300. Okay, so what I got here is one plate comes out at, or 1/2 the tube comes out at 22, and the other one comes out at 13. Now, let us compare these to what's on my spreadsheet. I'll have to add these numbers in too. These are all way too low. Way too low. So, let's repeat this. Okay, so we want to go to the other plate. I've turned off the high voltage. We want the high voltage back on. It's coming right up to 250 properly. Okay, so we're at the 1.1 mark, and I'm getting 2.95 milliamps. 2.95. I'm going to reduce this to 1 volt by turning the correct knob and not stepping in front of the camera. Down to 1 volt. I'm sure if you take too big a delta, you're starting to get kind of like averages, or it's not a good idea to get too big a delta in here. Ooh, there we are. Okay, so that's 1 volt. And now the current is 2.69. That's right. No, that's not right. How can that be? Jim, think. Okay. I'm having trouble thinking. Nothing new in that. 6, 1, 8, 2, 2600 this time instead of 2200. Yeah, 2600. So let's check the B plus and see if it hasn't gone up a bit. As soon as I grab the right test lead here. Yellow one, yellow one, yellow one. We don't want this on AC, we want this on DC now. Our plate voltage is 252, so I mean that's not going to cause a problem with the reading, that tiny change. I'll put it right on 250 though. Try. 249. Okay, and this is correct. And I'm sure the current in the tube is correct. 6. Everything is correct. So, you know, even when you look at something like this, it says 250. It could be 250.1. It could be 250.9. So, because this is flipping downwards, it's pretty close to 250.0, I would say. I think that's a good sign that I'm on. Well, I think that's close enough to 250. Never mind all the thoughts that just roared through my head there. Back to the AC signal so we can do the grid. Grid. So you still have a 1 volt signal on the grid. And that's yielding at 2.65 milliamps. This is the very same numbers. 2.65. Now we'll raise that. Raise that with the right control up to 0.1. 1.1. 1.1. Well, I don't think I can get much closer than that. 1.1. 2.9 is the current now. And this time we get 2500. So I've done this test right in front of you 3 times in a row, and I've gotten 2200, 2500, and some other number in here, 2600. It really raises questions. I'm repeating the test right in front of me here, and it doesn't seem to be the same every time I do it. Well, let's try it one more time. So this has remained at 250. 0.6 minus 8. Okay, so 2.92. That's just where it's been sitting. Sounds crazy. I'm going to reduce it. What if I reduce it half as much? I don't know if I can, because you know it's hard to, like, the smaller the delta, the more critical it is in measuring these amounts. So I'm not sure I want to do that. Let's just repeat and rinse. Rinse and repeat is what they usually say. That was my humor detector going off. Okay, this time the current is 265. It's exactly the same. Am I doing some stupid arithmetic here wrong? The difference between 265 and 290 is 25. 2500. 2500. We're all over the map. Let's do the other plate a few times. See if it's just as out of control. So we can start right here with this signal level, 1 volt AC, and get 157. I'll write it over here. And raise this up with the correct control. Okay, let's try that. 165. That's a difference of 12. That's 1200. 1200 compares with 1300. So I seem to get pretty good consistent results on the low end, and the higher ones going up and down. For reasons I didn't quite get. There we go. That's what's involved anyway in bench testing these tubes. I got a couple more I want to bench test and get them on my chart before I start studying the chart of numbers and try to resolve some kind of useful knowledge out of it. Right. So we're on to the next tube here. So here's the next problematic tube, tube number 10, and I'm just about to do the GM calculation. There were a couple of differences in this tube. It didn't draw quite as much current through the heater. I had to turn the power supply up a touch to get it up to 0.6. I wonder how much variation there is between tubes on this. The plate voltage seems to have floated a little high here. So again, because I'm doing my best to do this with some kind of reliability. No, 250. So we're actually okay on that. Okay, and we'll go back to grid. AC reading of 1.1 volts. So 1.1 yields a current of 1.05 milliamps AC. And we're going to drop this now to 1. Very cleverly turning the correct control. Okay, so there's 1. There's a 1, all right. Now the current is 1. The current, hey, 1 yields 1. That's interesting. 1. So that's a change of 0.05. You know what? This is going to come out to 500. The GM is 500. The typical GM on this tube is 2,000, 2,500. In that range. Okay, let's flip plates. Okay, not to worry about that. So we're starting at 1. Now we have a much higher current here of 1.31. So we'll raise this up again to another tenth of a volt higher. There we are. Now the current is 145. That's an increase of 14, so that's 1400. It's pretty easy to do the measurement right off that. 1400. So I got 500 and 1400 for this. Okay, so the test I'm going to do, after thinking about this a little more, is I've added in another voltmeter here, and this is reading the voltage across the heater. The reason for this is, up until now I've just been reading the heater current and I've been setting it for what is required. But no radio does this. Radios and other things, they supply a voltage to the tube and the tube draws whatever current it's going to draw. It should be 6 of one, half a dozen of the other, but we're testing tubes here, so we're looking for problems. So as you can see right now, I've got the proper current flowing through the tube, but it's taking 6.55 volts to do it. And this is the temperature. This is the voltage right at the heater terminals under here. There's no voltage drop interfering with this measurement. So in a radio, the output of the transformer, the 6.3 volt output, it's probably plus or minus a bit itself. And then you have, of course, your house voltage issues going up and down. That voltage will go up and down too. House voltages go up and down, say 5 volts out of 100. That's 5%. So you can find a 5% variation in the current flow in the tube. Something like that. And you know, it's the heat effect is the square of the current. So a small change can have a much bigger impact. So I want to kind of track this. I'm just thinking it through now, right here on the video. So I have an option of controlling the current and then reading the voltage. You know, I think that's what I'll do, because that way I know the current. It'll be the same for every tube. Then I can do the plate current test under standard voltage and standard grid, knowing what the current is, that the current's the same in every heater. And we'll just record the voltage, and that'll show a variation, enough of a variation that we can appreciate how much variation there really is in these things, including maybe, you know, a tube is older. maybe as it gets older, something happens here with this. I don't know. This is all about finding out what you don't know. Boy, I found out a lot. I found out a lot of stuff I don't know. So, so here we are, ready to do the first one. So I would record this voltage, 6.54. I gotta control this to this level. I gotta get this down to, like, you know, within a couple of numbers out here. I gotta be very, very precise if I'm gonna bother with this. And also record, it's hidden away here for view. Most importantly, the DC current flowing through the tube. That's on AC. How did it get on AC? We want it on DC. There we are. Okay, I think I'm all ready to go here. And I'm just going to carry on. I can run the entire tube set through this test fairly quickly. That's why I'm happy to do this. I might as well. Okay, that's good. That's good. Let's get going here. Let's get going, Jim. Get a move on, man. So I've made it my way to tube number 13 here. Tube number 13 is a half-dead tube. It's a complete zero on one half. And you can look at the current flow here, and you can see it's half the current that's required. So, you know, my supply is putting 7.2 volts on it to get that kind of current. Let me just crank this back just to show you how this works. So I'll crank this back to what it should be, 0.3. Only one filament is heating in this tube, so half the current is what you would expect. Same voltage though, should be the same supply voltage. Okay, that's close enough, and the supply voltage is 6.3, right on. So a lot of tubes don't meet the 6.3 volt requirement, I have discovered. So we're going to get zero current in one plate, and on the other 7.73. Onward. Now in the last tube, it took 6.3 volts exactly to get the right current in there, into the tube. This is the next tube. That's the proper current into the two filaments. The voltage that's required to do that is only 5.3. What happens if you put 6.3 volts on this tube? Let's find out. Put 6.3 volts on it. Okay, so there's 6.3. That's about as close as I can get it there. And you have 10% increase. The current flow is 10% greater than it should be. So the heating effect is probably 15% greater than it should be. Something like that is going on here. So I thought that was kind of interesting. That's why I turned on the video. So next is the next tube. We just keep going. Okay, well, let's take a look at all the results here. We'll take a quick look. I'll do much more analysis on this and see what I can get out of it. So let's just look at how this is structured again. So this is one of my testers. This is another tester, the big precise one, Stark one, the ICO, little ICO tester, and then this is me doing bench tests through here. Some comments along the way. Each tube has a tube number, and there's a plate 1, plate 2, and I've done my best to have this sorted out correctly. Plate 1, plate 2. Plate 2 is always the same plate, in fact. Well, it may have got some of these turned around a little bit, but hopefully not. So we just go across the first row here and look at the GM readings only. We'll skip these ones here. So 2832. See, now this means I did 2 tests, so look at that, it's all over the map. So on this test 2221, and on the next test 2125. So let's see what the Stark says. Oh, I did a couple tests in the Stark too. 2326, 2025. Here's my own bench test, 25 3000, 2500 3000. So you can look at that for quite a while and wonder, oh, all these different numbers are all over the place, really. But every one of them says the same thing, pretty loud and clear here. This tube's in pretty good shape, but it's not balanced. That's about what you can get out of that. We also go ahead and look at this. Here's the current test. Oddly enough, quite different. Let's see, you get a higher current, you get a higher GM. I don't know if that's true all the time. Let's just skip down the list here and find another tube with, so here's one that's got a variation in the current, tube number 7. So the higher current is here. Get to higher, higher, higher. Yeah, maybe that's maybe that. Well, I guess that kind of makes sense, doesn't it? Tube number 10. There's a low and a lower, and low and lower, low and lower, low and lower. So here's a number of tubes where during the test I noticed the reading was falling off. And this happens a little bit with almost every test, but not all of them. And some of them it's quite noticeable and would go on for quite a period of time, so that's why I noted this. Now what goes on? I got to just move this over a little bit here. It's a number that we'll hunt them down. For now, let's look at this one. So this value was falling, and just kept falling slowly, you know. Unstable tube. What else is there in here that makes me 4 and 6? So that's a pretty high number. That's the EM test. That's a high number. These are high numbers. The expected number here is around 9 milliamps in this test, and I think, you know, here's one up here that got there. There's another fall off. Look at that. Now this is a good tube to look at. It's really, look at 800 and 2300. This is number 15. So radically different. So what's going on in this tube? It shows up in the EM test also. And a fall off. I noticed it a number of times, falling. I was starting to realize it was worth keeping track of this effect. So hard to say what's causing it. I don't know enough about all the metallurgical factors and various things in the tube. But this would be a tube much more interesting, or it would be interesting to do much more testing. Notice the other side is not falling off, so I think we could eliminate gas in the tube. It's interesting. Anyway. Here's another one that's falling. Very low current and low GM readings, a low emissivity. These emissivities are still in the good on the indicator on the ICO. Can't remember for sure. I think it's 1600 on the Weston. Anything under 1600 should be scrapped. I think it was the same on the Precise. But I think on the Stark, it was 800. Maybe 1600 on one machine and 800. Where's the Stark machine? 800. I'll look more closely later. It does make you wonder, though, where all these numbers really come from. So the bottom line here is these tube testers can certainly tell you when a tube is really bad. And I wouldn't say this is the bottom line. I'll do a lot more analysis on this. But similarity between them, because of the variation in GM, because of the test conditions under which it's done. And I know, like for instance, the Stark has a particular circuit in it that was patented by the Stark company or whoever it was. Hickok, I think it was Hickok, and they used this special circuit, probably some kind of bridge circuit or something like that, to come up with these GM numbers. And I guess technique was so valuable that they got a patent to stop other people from using it. So how these other machines do theirs, unless they have a license from Hickok, isn't the same way this one's being done. Let's just look at the range here of current flow. So here we're like just under 6. They're all around. Oh, I'm looking at the voltage. Whoop, let's look at the current over here. This would be a better column to look at. I was going to say, wait a minute, I don't remember them being that low. 5. No, it's close to 6. There's a 4. So in these cases, probably what's happened is the cathode is giving out. It can't push out the electrons like it used to. Remember, the cathode is hot, and so it's chemically far more active than anything else in the tube. So if something's going to happen, it's probably going to be in the cathode. That's probably what it is. Just worn out. Probably a really high mileage tube. Yeah. Okay, and of course I had these box tubes. I didn't bother doing this testing with because I didn't want to take them out of the box. Well, here's a chart I did. This is comparing the Weston 981 GM test against the ICO 625 EM test. And so you see the EM scale and the GM scale. And I put this on here just to see if there was some relationship, and there certainly is. First of all, the ICO range, look at, they're all above 50%. So these are all passes. Everything passed in the world of ICO. If you trust the good and the bad, because it's just 50% where they split it. On the other hand, on the Weston, Weston was 1650, I think. So 1650 is somewhere here. So the Weston is saying these are all bad and these are all good. Can we draw any other conclusions? So no, generally getting better means moving in this direction, moving up this way. You see, generally, if one of them is saying it's better, the other one's saying it's better too. Generally, I guess that's what that slope of this line is kind of saying. But boy, you'll never sell a tube if you use an ICO as your tube tester. You'll never sell anybody a tube. And you'll buy a lot. Okay, I think that's enough talk. I think that's enough. I'm really worn out here. So thanks so much for watching this production so far. I really want to get back at fixing up a radio, or something anyway. So I'm going to think about that a little bit before I decide what I'm going to be doing in here tomorrow. So again, thanks a lot for watching this. I hope you're getting something out of it too.